Yes, Professor, you can go ahead.
Can you see my slide?
Yes, yes.
Full screen?
No, no. Display settings. Go to display settings.
Display setting. Like this.
Yeah, fine. Fine.
Okay, good. So, I think still morning in India, right?
Yeah.
So we are 4:30 here in the afternoon. So good. Thank you very much for joining back. So we will be looking into the, like I mentioned before, in this hybrid renewable energy systems, one of the most commonly components that is widely used is the photovoltaic system. And understanding how these photovoltaic systems works is very important to make sure that the microgrid success. Yeah, because sometimes we may maybe over design or under design this systems, and then that leads maybe to the overall microgrid systems will not be functioning well. Okay, so that's why it's understanding it is quite important for everyone, you know. So okay, first I think where is it? Yeah, need to get a pen. Yep. Okay, first one, these are the what you call the outline of this module, where we look into the PV, the components, then solar PV cells arrangement, because understanding how the solar cells actually functions helps a lot in understanding the overall systems. And then the PV sizing considerations, you know, how we consider the design, you know, the sizing, you know. For example, I want to design a 5 kilowatt system. Is my 5 kilowatt system based on solar panels, kilowatt peak? What will be the size of the inverter? What will be the size of the converter that we are going to use? So this is very important, because if you have a mismatching between the components, you will have a very low efficiency. Okay, so very important the PV sizing. You know, PV sizing, it's very important, because most of people actually thinks that PV sizing, okay, that's the PV panels and the inverters, and then just buy like that. You know, no, it is very important to know the matching. You know, because when you have a PV systems, for example, you have photovoltaic panels, and then you have the DC-DC converters, and then you have the inverter. As we know, the efficiency, if we have a system like this, the efficiency is the multiplication. So if I have 100% efficiency in the PV panels, 100%, 100%, then get 100%. If I have 100%, 100%, 50%, the total efficiency will be 50%. So it's a multiplication. All right. So that's why it's important when you have a system which consists of few components, these components have to be optimally sized. Okay. And then we look into the types of the PV systems. And then we will look into some examples on the PV system design for microgrids. Okay, I think we start with the first one, which is the solar irradiance. I think it's very important to understand this, because PV panels works on the solar irradiance, or the solar irradiance lights. Okay, so as we know, I think most of us know, you know, there is the power. You know, it's almost a million watts, or 10 power of the power that we receive from the sun. It's a huge amount. But however, there are a number of components actually which is being reflected, You might ask question why we have to study this, because this is very important, because later on we will see how we can maybe absorb these kind of lights, So some of it is reflected, some of it is reflected in the atmosphere, some of them it's reflected in the cloud, some of it is reflected by the Earth's surface. Okay, so it's a lot of reflections actually happens from the atmosphere up to the ground. Okay, once it reaches to the ground, okay, it reaches this amount of solar radiance. So we are not going to absorb all of it. Impossible, because this has different wavelength. Okay, it's not single wavelength; it's a different wavelength. Okay, and then the solar panels is designed, as you know, from semiconductor materials. Okay, and these semiconductor materials absorbs the certain wavelength only. It does not absorb the full wavelength. It absorbs certain wavelength. Okay, so the selection of the materials, that's very, very important. So that's why we are going to. That's why, for example, if you look into if you want to absorb more, then you will have different materials, 2 or 3 materials. We call them multi-junctions. So that actually helps to absorb the more power and become more efficient. So typically, solar PV systems consist of the following. Okay, so you may have what you call PV, which is a must. You may have a DC-DC converter, also an inverter, and then sometimes you may have a load, or we can connect to the grid. Okay, or sometimes we have an inverter to store this energy. So these are the main components of the system. Okay, and as I said before, it's very important to optimize the design of this and how you select correctly this kind of components. Typically this, because, for example, because the efficiency, this efficiency multiplied by this efficiency, multiplied by this efficiency, multiplied by this efficiency, multiplied by this efficiency, then you can get the total efficiency of the system. Because what we are interested here, we are not interested, because when you go and buy the inverter, they will tell you the inverter efficiency is 99%. Doesn't means when you put it in your solar system, it will get 90% efficiency. No. Okay, because the efficiency of the solar panels maybe is 20%. This one may be 98 or 96% efficiency. This is maybe 99. So the load maybe is 50%. So the efficiency will drop. It's multiplication. That's why I say very important to optimize the design of each component to get the maximum power from the PV system. Okay, so these are the major components, which is the photovoltaics, PV array, and there are quite a number of them. Okay, most of them, they will absorb certain wavelength, as I mentioned just now, and then convert that to DC electricity or power. And then we have the power conditioning equipment, which is mainly the inverter, and sometimes we may have charge controllers or DC converters. And then we sometimes, for standalone application, we may need the storage, because as you know, solar is intermittent in How about now? Okay, so maybe I think maybe when I move the
Actually, today only the settings have been changed in the book also. Go to the full screen mode, sir. Display settings.
How about now? Can you hear me?
Yeah, can you go to the display settings, sir?
Display setting. How about now?
Yeah, now it is fine. Go ahead.
Okay, thank you. So as I say, the main components, for typically PV systems, so you have the PV panel on the rooftop. For example, if you have a rooftop here, and then you have the junction box, okay, and then you have all the DC disconnect, so some protections, and then if it is grid connected, then you have a DC disconnect or circuit breakers, and then you have the utility service panels, the distribution panels, and then you might have the battery system. So typically, these are the components that we use. Okay. And we have what we call the BOS, balance of system. Okay, so we have the BOS, okay, which is the balance of systems. Sometimes we may involve some mechanical structures. For example, to put these panels, you need the structure. So that is mechanical, nothing to do with electrical. Sometimes we need the wiring. Okay, so we need the wiring. So I think someone need to mute.
Yes, Professor.
Okay, good. So this is the BOS, the balance of systems, where the conduits, and so on and so forth. So these are part of the systems, and some examples like the conductor, the wirings, the junction box, the disconnect switch, the fuses, terminal connectors, and the remounting hardware. So these are part of the BOS. So that's need to be installed. Okay, so if we look into the PV solar cells itself, so PV solar cells have gone through few generations. Okay, starting from generation 1, generation 2, and then now third generation and fourth generation, and so on. So there are a number of generations. Okay, so if we look into, for example, the first generation, we start with the monocrystalline, and then polycrystalline, and thin film. You can see, and then you can see the change here. Actually, the change here is try to reduce the cost of the PV panels, because monocrystalline usually use a lot of silicon. So one of the ways is to reduce the amount of silicon used. All right. So then move to the thin film. Okay. These are different what you call cells technology fabrication. So the difference is among the efficiency and the cost. So most of the time, usually monocrystalline usually performs better, but they are a bit expensive. Polycrystalline perform relatively lower than monocrystallines, but maybe cheaper in cost, and then thin film may be cheaper. Okay, and then we have the organic solar cells. The organic solar cells usually using organic materials, such as we use dye-synthesized small molecule based and polymer based, and then we have which usually used to fabricate the thin films, which is actually called the third generations. So basically, these are the types of what you call, if we classify them based on organic and non-organic solar cells. Okay, but commonly, the most commonly used usually is this, the monocrystalline solar cells, due to its good efficiency, and performance. And there is a lot of research actually on how to improve the efficiency of the solar cells. And this chart is from the NAR, the National Renewable Energy Laboratory in US, which they keep updating the solar cells. If you look into, for example, solar cells, you can see they are classified here into a few categories. The first category is the what you call the multi-junction. This is the multi-junction solar cells, and we have the single junction solar cells. Okay, multi-junction solar cells, okay, can go very high efficiency. Okay, so means can go very high efficiency, especially for space applications, for where I think someone need to be muted. So we multi-junction solar cells usually used for space applications and for applications which cost is not a factor. Okay, so that's actually the reason. So for example, if you look into this multi-junction solar cells, you can see it's reached around 47% efficiency in the lab standards. And there are but the commercial, the single junction solar cells, we're talking about something like this here, around 23, 25 efficiency. So this is because this is reporting all the solar cells either is in the research or it is in the market. So, but we also have what you call emerging. Okay, emerging, which is a new one, which is basically an organic cells. Okay, and then we have the thin film. Thin film solar cells, usually the efficiency is quite low. So we're talking about the maximum efficiency around 14-15%, So it's not much actually. Even the organic solar cells is keeping actually improving in the last few years. You can see, it's reaching almost 20, but this is a lab test. And the problem with organic cell is degradation with the time. So that's a big factor. Means if you get the efficiency, for example, 15, in 1 to 3 years time, the efficiency may be dropped to 10. And this is not the case for monocrystalline. Okay, so there is a lot of research on this. So in terms of solar cells, as I mentioned, the most commonly commercially available solar cells, usually it's a monocrystalline, and the efficiency is around between 14 to 20, 18, but this is commercial. But in the lab, you can go to 25%. The same thing for poly. You can go up to maybe 19 lab efficiency, and this can go up to 10, maybe 10, 11% efficiency, thin film. Okay, and the issue is always this: the warranty. Because usually, as I said just now, the efficiency drops, especially for organic solar cells. Okay, so the choice always, it's always the factor, the cost. What is the cost of the solar cells, and then how we select them. And each solar cells come with what you call this data sheet or characteristics, and very important to understand how these characteristics actually can be read and can be understood. For example, here we have a combination of 4 types of solar cells. From one is monocrystalline, polycrystalline, and monocrystalline. If you look into here, what you can see, first one, the power rating. Okay, mainly the monocrystalline usually have higher power as expected. Okay, voltage can match, and the area, the area also can be almost, we're comparing the same area, So when you compare the same area, the same size of the module, you can see actually you get a higher power, okay, and also higher voltage compared to slightly higher voltage, but the power means the current is quite high. Okay, so for example, here it's talking about, for example, another type of solar panels. You see the lower power, low voltage. Okay, and then different Sharp, Kyocera, Evergreen. These are different manufacturers of solar cells. But they give a different rating and different voltage. So I think all of you knows how the PV modules actually is made or fabricated. It's all started with the solar cells, and the number of solar cells are combined mainly in series, okay, series to form the panel, okay, and then we have few panels combined in series and parallel to form what we call the PV systems or the PV array. So the number of solar panels will form what you call an array, okay. All right, and then this PV array, then it's will be able to generate what you call an acceptable amount of power that can be used or can be converted and fabricated. So actually, if you look into here, these PV panels, what you call solar modules, you can see it consists of a number of cells connected in series. So if one of the cells, for example, this cell is affected, so the whole module will be affected because they are connected in series. So once, for example, this is burned or spoiled, whatever, so this actually can affect the whole module. That's why what you call maintaining or forecasting, especially the fault detection in the PV panels is becoming very, very important. Okay, how we can detect that's one of the modules or what you call going to have a problem. So because that actually impact the total power generated from the PV panel, because as I say, it's connected in series. So this is out. And then when you put this PV module maybe in series, maybe with another module or parallel, maybe have less effect. But if it is connected in series, we'll have a major effect on the performance. Okay, so actually there are few components that comes with this PV system. Depends on the applications. You may design it for battery charging, so you need charge controllers. You may have a DC, what you call connections and so on. You may have a tracking system that can be used also. That's as a so PV system sizing. How much power do we need? So this is always the biggest question, So if I have again, we're talking about the PV systems in microgrids. So how am I going to size my PV system? Okay. So there are actually a few steps and a few measures need to be done before we can get the correct size of the PV panels. First one is the energy use and energy auditing. Okay. So before installing your systems, you have to do what you call energy audit. I'm not sure how many of you knows what is the energy audit and then how to do it. Anyone knows what is energy audit? I'm not sure everyone knows or not. Anyone knows what is energy audit?
Yeah, knowing about the losses.
Sorry?
Knowing about the losses in the system.
Okay, the losses. Anything else?
The estimation of that what the power capacity is required and what will be the usage and the associated losses and all.
Yeah, actually, energy audit means actually you know where the energy comes from and where it goes. That's the basic definitions. How much energy comes in and where it goes. And okay, for example, including calculate the losses, including the what you call the usage. For example, I use the aircon, how many hours a day I use the aircon, how many use I use the fan, how many hours I use the lights, and so on and so on. So this is what we call energy audit. So you have a profile of your loads and your source, And why this energy audit is important? Because without doing energy audits, you wouldn't know actually how much you need and when do you need. For example, there are some, because once we have the energy audit, we have what you call energy, what do you call it, energy conservation measures. Because there are some steps where we can do, we call it energy conservation, where zero investment. And that will reduce our energy consumption. For example, when you have you live in a room, you switch off the lights. So actually, that is a zero investment. Just turn off the lights. So that is, you reduce your energy consumptions. For example, if you are setting your air conditioning to 16 degrees, and then you bring another jacket to keep you warm. So that's a double loss. So, but if you set the air conditioning at 24 to 25, actually it's a comfortable. That is the comfortable temperature. So actually, increasing the temperature to a certain level reduces the amount of energy consumption. So, and that doesn't need any additional investment. So by reducing this, you don't need to install additional photovoltaic systems or whatever. So that's why energy audit is the number one in any PV system design, that we need to do energy audits. Okay. All right. So that, and then energy use, where the energy is used, because sometimes, for example, you have your peak load. Does it happens during the day? Which time during the day? Is it at night? Because that actually influences the sizing of the battery and on. So the two components are very important. Okay. Use this. Yeah. So these are the components. First one is the energy use. The second one is energy audits. Okay. Energy use and energy audits are very, very important, because there are a lot of savings can be done after this energy audit report happens. And then we can look into what we call energy efficiency measures. Sometimes we may have light bulbs which are 60% efficient. So you have to look into your loads. Are your loads efficient or not? Or can be do some small investments? Because if you have for example, if you are powering all the lights and the lights are 60% efficient, so actually 40% of energy is lost in the load. So upgrading your lighting, for example, to maybe 90% efficiency actually save you 30%. And that updating the lights maybe is cheaper than installing larger PV systems. Okay. And then energy requirement for the PV. So that's actually quite also, as I mentioned just now, that's the load matches the peak of the PV panels. Okay. So I hope it's clear this. So because this is quite very important measures before even discussing what we should do. Before discussing what is the size of the PV panels, what is the size of the inverter, what is the size of the battery. So these steps have to be done first on our existing loads. And then based on that, we will then need to decide on the size of the PV systems. Okay? So these are some considerations that need to be done. First one, begin with the precise calculation. When you see precise here, we're talking about what you call for example, the load size, the number of hours that operate during the day, which hours during the day it's operate. That is what I call precise load calculations. Okay, a reduction of load requirements, if by efficiency measures, like we said just now, for example, reducing the lights. Maybe your air conditioning is time to change. Maybe you change with an inverter-based air conditioning. You are changing your washing machine. Maybe you have to promote an inverter-based washing machines. You have a cooking. Maybe you can go to electric cooking, instead of using gas. So these are the efficiency measures improvements. Okay, because that will has a major impact on the PV system design. Okay, and then estimates. We have to do the estimation based on the data of the irradiance that we have. Okay, so as I mentioned also yesterday and again, renewable energy systems are location specific. Means they work specifically for specific locations. Okay, means what works in India may not work in Australia, and what works in Australia may not work in India, because it's a location specific. When I say location specific, means it's the amount of irradiance, because the temperature, the direction of the sun, the clouds, the clearance index, and so on and so forth. So there are many factors that affect the performance of the PV systems. Okay. All right. So that's the number 3. Second one is select the hardware to match the load requirements, which we will discuss. Actually, select the PV hardware. Here, the PV hardware, we're talking about the number of panels, how many panels you need. Okay, what is the size of the inverter that you need, and so on and so forth. Let's match the load. And then you need to examine previous power bills. That's also a good indication to see actually how your power consumption in the previous years, or previous months happens. And very important to look into this, because sometimes the power consumption depends on the seasons. So I'm not sure India, which location you are, but some countries, they have winter, they have summer, So in winter, we will have very high cooling, heating loads. In summer, we have very high, cooling loads. And maybe if it is a tropical country, it means it's all cooling loads. If it is very high, very cold, means it's all heating loads. So these are good considerations, because sometimes, for example, heating loads always comes with low solar irradiance, because it's cloud and raining during winter. High cooling load always comes with the high power, which is during summer. Okay, so sometimes the load matches the source, and that is good. That's why you need to do this. Okay, I think that's already clear up mentioned. Estimate the potential. I think we already discussed this already before. Okay, choose the percentage of load to match. For example, we are not going to design a PV system that supplies 100% the load. It's impossible, because it would be too big, too huge. Okay, and that's the thing. And then last one, which we mentioned just now, which is the hardware selections. Okay, any questions here so far? Any questions before we move?
There is a question in the chat box, Professor.
Okay, let me check on the chat box.
Can I read out it?
Let me check the chat box. Where is the chat box? Yeah, here. Please put up your questions in the chat box,
Next,
calculating how much power we need. I don't know. I didn't understand the question, because the question is not really clear. Calculating how much power we need.
It's not the question, sir. It's the answer what you were asking for energy auditing, I think.
Okay. Sorry, I think that's correct. You're right. Maybe anyone have any questions or comments, before we move next? I don't know, Dr. Siva, is it possible that the audience can they mute and unmute themselves, or not possible?
They can mute it also. I think.
Yeah, I think you can unmute and you ask the questions. Please.
Yes, sir, we can.
Okay.
The PV installation in the microgrid. I have one question, sir. I mean, what
Sorry?
are the? I have one question.
Yeah.
In installing the PV in a system, what are the major things need to be considered?
Yeah, the major thing to be considered is, as I mentioned, is the sizing. What will be the size of your PV systems, and that's the biggest what I call challenge. To define the size of the PV system that you need. And as I said just now, energy audit is number one step that we have to do. Why? Because sometimes when you do the energy audit, actually, you may not need the PV. Sometimes the PV is not the solution. Maybe if you need if you find that maybe I do the energy audit and then I calculate the costs, and then I see the cost of the PV, and then maybe the energy audit can give you because the energy audit usually will give 3 recommendations: 0 investment cost, medium, or we call it low energy cost saving, low energy cost saving, and then medium and high. 4. Sorry, we give 4 recommendations. Okay, so based on these 4 recommendations, for example, if you apply this 0 investment, for example, 0, you don't have to invest anything. So sometimes you have medium investment or low investment. Low investment means you may need maybe some sensors or some, turn on and turn off, reducing the temperature or increasing the temperature of the air conditioning, and so on and so forth. Okay. So the sizing is the most important, crucial component in microgrid design of the system. Okay. I think there are another 2 questions here. The PV panel is connected to the grid tight inverter. What are the major problems coming into the picture? Well, yeah, there are a lot of problems coming to the picture. The first one is the connections. You need to satisfy the international standards. For example, what is the total harmonic distortions, the frequency. You are injecting a lot of harmonics to the grid. So there are a lot of issues actually to be addressed. We will discuss some of them later on the grid connection systems. Okay, so but there are quite a number of issues when we connect to the grid. But because, as you know, the inverter is operating on switching, turning on and turning off. So there's a lot of harmonics. So there is standards. There is that need to be followed. There is a PV classification for 1, 2, 3 diode models where can have a real-time application for those diodes in PV. I'm not sure if you are referring to the bypass diodes that we inside the PV modules. If you are referring to these diodes, we will see actually what's the importance of these diodes. These actually called them bypass diodes. These diodes actually meant for protection. Means if one of the cells, for example, burn or become a hotspot, so what happened? That cell become a resistance, and that means the current that all the cells throughout that one will be dropping through that cell. Okay, so one of the ways of solving these problems is to have a bypass diode. So you group a number of cells. Okay, maybe 6 cells, put bypass diode. 6 cells, put bypass diodes. So like this, actually, you can reduce the impact of in case of one of the cells. If I understand the question correctly, that's the way I call the bypass. But this bypass diode create another problem, which we will see later. So, but this is one of the ways on how to, to bypass some of the cells in case there is a fault. But the ideal case is to put every cell 1 diode, but that's not possible because the cost will be very expensive. So that's why they group a number of cells, put one diode, group of cells, one diode, and so on and so forth. Okay, I think if there's no questions, maybe you can resume. Okay, let me share. Okay, display. Okay, I think it's clear, right? So I think one of the key decision that we need to make is the PV module placement and orientation. Okay, because that has a major impact on the amount of panels, amount of power that is produced from PV panels. Okay, where to place it and the orientation. So the placement, it's very important. So because, for example, we need to study the impacts of shading, the area that has shading, because shading will impact the PV panels, the sun path. That's why I say different locations will have a different sun path. Okay, all right, and that's very, very important. So the azimuth and the tilted angle. So these are some of the key parameters actually that need to be considered when we do the PV panels or the PV system design. Okay, so for example, tracing the sun. So usually we use this Pathfinder tool. This is how it looks like. This one. This actually Pathfinder, So this actually will gives you, you put it in the location, it will give you the obstacles to the sunlight and and the season change, because sometimes we have the winter, summer, and so on and so forth. So this seasonal variation also impact the amount of sizing of the PV systems. So this is the must use. This is what we call solar pathfinder. You have to put in the locations, and then you can study the pattern of the sun. And because that will help you to the orientation of the sun. Also, I think PV module placements and orientation. Also, the standard PV module, which is the azimuth, which is the orientation. It's we call it the true south. And also we have the PV module tilted angle. Okay, this tilted angle, it's very important. Okay, what is the best tilted angle? Okay, and this also varies from location to location. So usually it's plus or minus 15 degrees. Depends on it is plus 15 degrees for winter, minus 15 degrees for summer. But this one need to be studied and need to calculate what is the best tilted angle. And this tilted angle actually have a multi-objective. It's not only to maximize the power to the PV panels or maximize the absorption, but also it helps also in the cleaning of these PV panels. Because once these PV panels, put at a certain angle, because when it rains, it's automatically auto-clean. And also the auto-clean, and then also, for example, especially in cool countries where you have winter, a lot of snow. So this actually helps the snow to slide and though, because that otherwise it will break, because you have a heavy load on these PV panels, So actually, it has a multi-object, and also cooling, because once you have a certain tilted angle, actually the wind can blow underneath the PV panel, and that cools down the PV panel, and that improves the efficiency of the PV panel. So actually, it's multi-objective. Okay, it's not a single objective. Yeah, the main objective is to maximize the power absorption. However, as I say, there are other objectives which I have mentioned just now. Because, for example, if it is the dirt accumulate on the PV panels, that actually can reduce maybe by 10% or 15% of power. So you need cleaning. But if it is tilted and then there is a rain and then it's auto clean, you know. And also even for cleaning, you can just spray water and it auto cleans, you know. Compared to have it what I call horizontal placement. Okay. So maximize the energy production actually by optimizing the angle. So this is, for example, if winter, you may have also some summer, you know, and then spring and the thing. So this can be done if you have small systems, but sometimes it's difficult to do this because this is called tracking, you know. So you may have a tracking. You may have tracking, which helps you to track the sun, but that is an electromechanical system. But that one is maybe too expensive to implement and too complicated. Most of people go for fixed structure, okay, which is around 15 degrees actually. It's facing this, like here. As I say, depend on the locations, you know. Okay. Okay, and then if you can adjust, that will be the best to maximize the PV panels. So some, like I said before, you may have a fixed structure. This is a roof mounted, and this roof mounted, you can see it is a retrofitted roof mounted. Retrofitted means you have an existing roof, and then you put the panels on the top of the roof without touching or modifying the roof. This is called retrofitted, because we also have building integrated. Building integrated means instead of the roof, you put the PV panels. And that actually helps also reduction of the cost of the PV systems. Commonly you use this PIPV, but for existing homes, you cannot remove the roof and then put the PV panels. So we use what you call retrofitted. Okay, but if you have a new home to build, I think it is worth to consider putting PV panel inside of the roof, putting a PV panel inside of windows, and so on and so on, because you have transparent, semi-transparent windows, you know. So actually, so it means you can help mounting this. Okay. Also, we can have a ground mounting. It's in the ground, so this one, and also we can have a trackers. You can see here. This is actually a tracker, and here is the tracker. So this is a 2-axis tracker. Means you will move, you know, in 2 directions to track the maximum power from the PV. This is called electromechanical tracker. It follows the sun. Okay, but as I say, sometimes this mechanical cost, you know, these tracking systems can be very expensive, and also the challenge is to power, because these are large motors. You know, to move these motors, you need a lot of energy. Sometimes the power that's generated from this PV panel is not enough even to move the motors, you know. So this is one of the, you know, mounting options that we have. But the best will be also automatically the trackers. But as I say, it's not, from my opinion, it's not practical. Okay. Okay. So during the installation of these PV panels, we need to PV cooling, as I said before, because as we know, the PV panels are made of semiconductor materials. Okay, and semiconductor materials in general, they are very sensitive to the temperature. All semiconductor materials. Okay, because you know, semiconductor materials, you know, is made of p-n junctions. You know, I think all of you know this. You know, the basics. You know, so the moment this heat actually build up in these junctions, then it will behave what you call very you know, not really regular. You know, so it means that's why the PV panel efficiency drops as the temperature increases. And here, when I talk about the temperature, I'm not talking about the ambient temperature. I'm talking about the cell's temperature. cell's temperature is inside. So because you have solar cell, and this solar cell is covered by glass. Okay, and this glass, under the glass, okay, so the temperature can be easily, for example, if you see the temperature is outside, the ambient temperature is around 30 degrees, inside the cell can be easily maybe 50 or 60 degrees. So, and not only the due to the glass coverage, but also due, because as I mentioned just now, there are some photons, These photons, in order for them to generate the electrons, they need to cross the band gap of the materials. And some of the photons, yes, they have enough energy to cross the band gap. Some of them, they don't have enough energy. Some of them, they have extra energy. So that extra energy actually becomes heat. So this is the basics of the PN junction, how the PN junctions, because once the light heat up the panels, so you have three types of photons. We have photons which has an energy less than the energy gap. We have photons which has energy equal to the energy gap, and then we have photons which has an energy greater than the energy gap. The best one is the one having equal energy. But sometimes you have photons which have higher energy, so the extra energy will be dissipated in a form of heat, and that will heat up the cells, and that will reduce the efficiency of the PV panels. So wind resistance, this is very important. So when you design your PV systems or for these microgrids, you need to make sure wind resistance. Otherwise, because I'm not sure in India, but here in Australia we have a lot of wind, high wind. So wind resistance is okay. Structural stability, okay, very important. The structure have to be stable, okay. Code compliance, okay. So we have each country actually has a code that we need to comply. For example, if you have a grid connected, you have a code that you have to follow. You have if it is standalone, you have a code to follow, and safety regulations, fire, and so on and so forth. Okay, and PV orientation, I think we have discussed before. Okay, and then it has to be visible to the audience or to the public, so in case is there any issues. Okay, so this is basically some of the considerations that for the PV. Okay, so maybe I think before we go into the storage, if we look into the PV inverters, the PV inverters can be classified into few of them actually. Okay, so it ranges from, because we have the PV and then the next one, which is the inverter. Every PV needs an inverter. So they are classified based on the power rating. So, for example, it ranges from 300 watts. 300 watt, I'm talking about 300 watt means actually a single panel, to kilowatt level or megawatt level, even megawatts. So, for example, here for low power, so we have what we call AC module, or we call them micro inverters. So this inverter is integrated with the PV panel actually. Okay. So it's integrated with the PV panel. So we call it micro inverter. Usually it's a low power. Sometimes we may have what you call a single stage conversion, like here, DC to AC, single stage conversions. Sometimes we may have what we call two-stage conversions. Okay, for example, DC to DC and then DC to AC. Yeah, again, each topology has its advantages and disadvantages. So that's for example, if you ask what is the best, which one is the best here? So here, it depends on the PV. So you have a DC and then you have AC directly. So it depends on the power that is available from the PV panel, and then you get out. But if you have dual stage, yes, there is a losses, but this you can configure this to operate as an MPPT. So what does mean MPPT? Means you can extract the maximum power from the PV panel. So you can have more power. Okay, so that's why I say there is pros and cons of each of the topologies. Okay, and then we have the PV string. Okay, so we have a number of PV panels connected in series, and then you will have an inverter here, string inverter, and then you can connect here. And this can be single phase or three phase. And this is for small systems. Small systems means like street lights, like small water pumps, fountains, and so on. This is 1 to 10 kilowatts. It's usually what you call usable for residential applications, which matches the power actually, which is 1 to 10 kilowatts. Okay, which is PV strings. We also have what you call a multi-string. Multi-strings, you have a number of PV panels connected in series, and they come out with their own DC-DC converter here, and then they have another DC-DC converter here, and then you connect DC, and then you create a DC bus, and you have an inverter, and then you connect. This also can be single phase or three phase. And then the last one, where you have a PV strings, where you have series, parallel, and then connect to one large big inverter. Okay, so and the applications is also the same. You can see commercial and utility scale. Utility means it can become power plant. Talking about megawatt, 10 megawatt, 20 megawatt, 30 megawatt, even gigawatt level. And this is mainly for commercial applications. So, okay, so maybe we can pause for 2-3 minutes for questions. Any questions? We have 30 minutes. So any questions? Maybe I will look into the chat, because we discussed a few things here now. Maybe participants have any questions to ask. Any? Please unmute your mic, and you can ask, or you can write either one. Because it's very important to understand this concept, especially on this PV. So how you see like the inverters, and then what types of the inverters, or if you have no questions, I can ask you questions then. Okay, if I want to ask you questions actually. What is the advantage of having a micro inverter because here you can see central inverters we have, or maybe the question is maybe simpler question. Which one is the most cost effectiveness here? Which is the most cost effective system? Because if you are talking about microgrid, the cost is important, right? So which one is the best, the most cost efficient option here?
The central inverter.
Yeah, the central inverter, yes, is cost effective. Yes, very true. Which one is the best in terms of power? What you call extraction, or the power in terms of power extraction from the PV? Which one is the best inverter?
I think, the string inverter.
Anyone? The best one will be the modular inverter, because this is every inverter one module. Means if you have 10 modules, you have 10 inverters. But this is a part of the panel. It's the inverter actually is not a device, but it's installed at the back of the panel. So what you get is the AC. So what does it mean? It means if, for example, one panel is shaded, so what happened? Only one panel will affected. But if you have a string inverter, if one panel affected, the whole string will be affected.
Okay. No, but the modular inverter is you have a circulating currents, is it not, Professor?
No, that's not an issue. we don't have an issue in any of circulating current, because what you have in here, I'm talking about what is which inverter that we can extract the maximum power from the PV panels.
Okay.
You know, because this you'll be connected to an AC bus. Automatically, the current cannot flow back to the PV panel anyway. There will be no issue of circulating current among this. But in terms of efficiency, and this here also you can address the problem of MPPT, because once you have PV panels like this connected in series, individual panels will have a different operating points. Okay, because we have the IV curve, which we discuss later, the IV curve, you know, and the power curve. In that power curve, different panels will have a different curve, so you will not extract the maximum. But the problem with the microinverter is the cost, because it's very significant, because every panel requires an inverter. So that's why we said actually the best option is either it's a string or multi-string. Central inverters, usually they are very low efficiency, because you can see a large PV panels connected to single what you call inverter, and that actually you lose to operate at the maximum power of the you know. Okay, because
it is difficult to track the MPPT from all the panels, right, sir?
yes, but if you have a microinverter, yes, you can.
The central
Right.
inverter.
Yeah, central inverter impossible. Yeah, you cannot do that, because where you want to track the maximum power, it's here, because different panels here they perform differently. But as I said, is in terms of cost effectiveness, this is the best choice in terms of cost, because we usually call it per kilowatt, dollar per how much dollar per kilowatt. So you will find that actually the central inverters having the lower cost, and this string and multi-string is something in between the macro inverters and the central inverters. It's not too big and it's not too small. So means trying to match between the two. Okay. Any other questions? Participants, any questions? Multiple. Yeah, I think the answer. Yeah. Any other questions from the participants? Okay. If no questions, maybe we continue. All right. Share. Now full screen, and then slideshow, present everywhere. So I think everyone knows now. No, I know how to do it now. Okay, and if we look into now, we're talking about these inverters here. Okay, these inverters. Okay, in these inverters also, there are a few selections or few configurations actually we can select. So we have few of them. Either is it a transformer based or transformerless based. Okay, this is another what we call question. So if you look into this transformer based, what does mean transformer based? There are two options. The first option is to have because this is you need to know all of this for you select the inverter. Where is my mouse? Yeah, it's here. So we have a frequency transformer here, which is a low frequency transformer. Okay. So like here, you have the PV, you have a DC-DC converter. This is optional again. It's not necessary. Okay. And then you have an inverter. Okay. And then in order for you to connect to the grid, you need the what you call low frequency transformer. Low frequency transformer means it's either 50 hertz or 60 hertz. When we see 50 hertz or 60 hertz means it is very bulky. Means it's the power. As the power increases, the transformer size increases. There is another option where we can have what you call a high frequency transformer, because these transformers are very important, because they provide isolation, galvanic isolation, in case there is a fault here. This fault does not go to the grid. It is a grid fault, does not go to the what you call, to the system, to the PV system. So also we can opt to have a high frequency. The good things of a high frequency transformers is the size, because I think all of us knows the size of the inductors, capacitors, the passive element, it depends on the frequency. As we increases the frequency, the size of the inductors and capacitors gets smaller. Okay, so, and transformer is just like an inductor. Okay, it's a simple inductor, two inductors, So to increase the frequency, instead of 50 hertz, we increase it to 20 kilohertz, and we can reduce the size of the transformer. So then you will have a PV, okay? But this PV here, then this inverter here again, this is not a normal inverter. This is a high frequency inverter. It has to generate a high frequency for this transformer. Because this here, this inverter is a low frequency inverter. It generates the 50 hertz. But this one here, it depends on the size, maybe 20 kilohertz, 50 kilohertz. Huh? And then after that, you will have a rectification, okay, DC, and then you will have the 50 hertz, which connect to the grid. Okay. So in terms of size, the high frequency based system is smaller. However, what you can see here, we have added another conversion stage, which is the rectification. Okay, so we have added this. So we have added the losses. So this is like I say, there is no one perfect topology that can give you everything. It's always merits and demerits, and then which one is better. So high frequency is good. However, we have introduced another level or another stage, okay, which is the rectification, which does not exist in the low frequency. Okay. Also, we have the transformerless topologies. And this topology actually does also, exist in the market. You either you're looking for transformer or transformerless. For the transformerless, you can see we have eliminated the transformer at all. Okay, but here we have lost the in terms of efficiency is better, in terms of size is smaller, but the problem is there is no isolation. So the problem of leakage current, it's an issue. So here, if we are able, there are methods actually on how we can control the leakage current, okay? Because in terms of safety, then it becomes an issue, very, very, very unsafe. So, controlling this is, it's very important, so to control the leakage current and the common mode voltage. So these are quite important factors, in order for us to design. So these are the two grid connection options, especially for grid connection applications. It's either transformer based or transformerless. Within transformer, we have two configurations: low frequency, high frequency applications, high frequency transformers. Both of them are good. They provide good isolations. However, the high frequency actually has another conversion stage which gives a low maybe efficiency. The transformerless is another option which is small, efficient. However, in terms of safety, it's a concern, which is problem of leakage current issue. So those are the configurations that we see. Okay, I think we talk about the grid connections. The standalone operations, okay. This standalone means when we have the inverter which operate independently, okay, of the grid, means maybe battery systems, okay. But when we have utility interactive, or we call it utility interactive, or grid connected, or whatever, or grid connections, the same things, okay, and supply the power from with the utility, okay. Also, we have bi-modal or battery-based interactive inverters, which operate in both. Means you can operate battery chargers, you can charge the batteries, and also you can supply the load. These are some inverters, actually, some inverters. And before I go there, I want to show you some examples of called inverters, existing. Okay. Let me, in the meantime, if you have any questions, you feel free to ask.
Yeah, sir, I have one question.
Yeah, please.
You explained regarding different topology with transformer and without transformer.
Yep.
I just need to understand which topology is widely used for industrial purpose.
For industrial purpose is the frequency based, what do you call it? Low frequency.
Low frequency transformer based.
Yep.
Okay.
The traditional one, the most commonly now used, is all on based on transformer based. Okay.
Okay.
Due to few reasons. First one, it is isolation. Okay. And then, especially, I'm talking here about large PV power plants. Okay. Because when you're talking about a few kilowatts, also you can use the transformer base. In terms of safety, it's good. It's quite reliable, and it comes always with the central inverters. It works with the central inverters quite well. But recently, in the last 5 years, a lot of companies like the SME, they start introducing transformerless topologies. Because the main issue for transformer topology is the leakage current. Okay,
yeah.
That has been already solved. They have already minimized the leakage current to a safe level, which is I think around 200 milliamperes, or I think less than that. So they have managed to reduce the leakage current to a safe level. Okay, and that's actually make them they will be a very important player in the future. High frequency and transformers, because in terms of cost, because if you assume you have a megawatt level, so you need to have a megawatt level transformer. Okay.
Yeah.
So that is a huge saving in terms of cost and maintenance. Is this clear?
Yeah, this is clear, sir. And my second question is related to the same. When we do the system study, considering the renewable sources like solar, so visually we consider that since this is power electronics best, it will not feed to the fault. I mean, when there is a fault in the grid side, there is a isolation and there will be no contribution from the solar plant side. But now I understand from here you explain. Suppose if we are going for either low frequency or high frequency topology, then in that condition, it is true it will not feed. But when we go for say transformer less topology, then in that condition, the solar plant will also feed to the grid fault. Is my understanding correct, sir?
Correct, very correct. Because in the transformer-based inverters, the total isolation, because the fault cannot transform through the transformer, right? Okay?
Yeah.
So in the transformerless, yes, the fault will be because I don't know. You can make it there. Yeah. In transformerless, so it's connected directly to the grid. The PV is connected directly to the grid. Power can flow. So that's why I say here, these other control techniques means you need to be able to detect the fault on the grid, okay, and isolate your system. So that means actually here becoming the control become more complex compared to the transformer based. So because the problem, for example, the grid, for example, sometimes you have what you call transients, not a fault actually, it's just transient, So how you can differentiate between transient and fault? And your control system should be able to determine actually, is this a fault? Is this because if it is a fault, you need to disconnect your PV systems from the grid, immediately. So fault cannot be transferred. And the issue also, you have to reconnect later. When the fault goes away, you have to reconnect. So you have a lot of connection and disconnection, So here in the transformerless, the control plays a very big role in having a safe grid connected systems. But I think it's not an issue anymore because now we have a very fast controllers, very advanced controllers, which we can use, and they can respond fast to this kind of events. Okay. All right. Good.
Okay. Thank you.
Okay. Any other questions? The audience, any high frequency operation will not lead to more losses, sir? Very good question. Yes, that's very good. High frequency, yes, actually, when we increase the frequency, the losses increases because the switching. Okay, that's very, very, very true. Very true. However, okay, if we are able to operate the what you call the inverters at zero voltage and zero current switching, then we can minimize the switching loss because we have what you call turn on. We have turn on losses, switching losses, and turn off losses. Okay, so we have this type of losses. The major one is the switching losses. So if that's why what we do for high frequency, we need to switch at zero current or zero voltage switching. So when you see zero voltage and zero current switching, actually your power loss will be almost zero. Okay, so actually that will help in reducing the losses. And you are very right. As the frequency increases, the switching losses, if we don't apply soft switching, automatically there will be losses. Yeah, one thing in research, this is based on my last 35 years experience. When you introduce anything new, you introduce new problems. There is no perfect solution. Yeah, you solve one, for example, transformerless. We remove the transformer, right? Many years, 10 years, 15 years, researchers are working on transformerless, how to solve the problems. But the problem of safety. So we need to solve the problem of safety. How to drop the problem of safety? Then we need another research. So this is how research is built on. Everyone comes, introduce, improve on something, but that things have some demerits, and then that's actually the problem for new research and so on and so forth. So that's how it goes. Okay. Any other questions? I think we had a good discussion. Any other questions from the participants? Please speak. I only see familiar faces from yesterday and today, asking the questions. So I would like to hear by the 5 day. I will hope that everyone asks questions. And I know your levels are different. There are some of you are PhD holders, some are masters, some are the bachelors, some of them industrial experiences. I know the standards, the expected, even for me, is difficult also to conduct a course when you have a very high, margin, from assistant professor to students, So there is a big gap. So, but as I say, there is no dumb questions. There is no stupid questions. Please ask. and I will be happy to answer questions based on what you need, All right. And let me, I think this is a good question about the high frequency. And then also what actually promote this transformerless with high frequency is also the advancement in device fabrication. Device fabrication. So we moved from silicon-based to silicon carbide and GaN devices. Silicon carbide devices, usually they will have less switching losses or lower switching losses compared to silicon-based. So you see, the advancement in device fabrications helps actually in pushing because they can handle higher power, they can handle high temperature, and also they can operate at very high frequency and with the lower losses compared to silicon-based. And this is also plus the soft switching techniques, which can be used. All right. Any other questions? Or okay, maybe we still have another few minutes, so maybe we can go here. Share. Let me share again. I'm sharing actually. Oh, I'm sharing here. So let me go. Yeah, just now I passed this too. Let me go to the storage, But the storage will be another topic anyway. Okay, so slide. So, like in the PV system, sometimes we may, as I say, we may include this storage and batteries, which is usually the primary source, of the energy that we use. And then also there are others like supercapacitors, the flywheel, fuel cell, and hydro. But this is for large, like hydro dam, we call pumped hydro storage. That's actually the most, if you ask me, is the most economical and the most efficient way of storing energy is the pumped hydro storage. So again, the same thing for the solar cells. Okay, the batteries usually they're being combined in series and parallel to meet the voltage. They can be made of lead acid batteries, which is cheap, okay, and variable. Also, we can have lithium ion or whatever other batteries, different types of batteries which can be used, and together with the just now the inverters. Sometimes, as you see, we have a batteries, so automatically we need to have a charge controllers, okay, and then battery chargers, DC converters, and the new trend now is not to have like this. Last time we have one charge controllers, we have inverters, we have DC converters, but now is coming to one device. We call it hybrid inverter. The recent developments is hybrid inverters. Means this inverter able to operate on grid connected and isolated, able to do MPPT, able to do battery charging, and so on. So we call it a hybrid inverter. Okay, no more few controllers or few devices, because the integration, as we said before, this integration actually may help to reduce the losses. All right, good. Yeah, so some examples. Okay, for inverters, and maybe before that, I want to show you before the micro inverters, which I have some. Let me maybe stop this one. Stop sharing. Let me share the micro inverters. So I'll give you some examples of some inverters. Micro inverters usually, where is it? Micro inverters. Wireless. Yep, this one. Yep. Yeah, I think I will show you this because this is also very, very, very important. Yeah. Sharing, presenting, entire screen, this one, and then, okay, this, and then goes to the MPPT just now. So remember just now we talked about this, remember? About the central inverter, multi-string, string, multi-string, and then microinverters. Okay, so if you look into like the central inverters, I think I need to, yeah, sorry, slide mode show, display. So this is what we mentioned just now. Sorry. And yeah, so we mentioned this central, multi-string, string, multi-string, and then microinverters. Okay, so what are the advantages of each one of them? So because the advantage is low cost per watt, relatively high efficiency, but they have the problem, which is the miss MPPT, no panel level monitoring control, difficult to expand, you know, and then high voltage level. You have to operate because it's a very huge inverters. So this is how they look like. You have a big power plants, solar power plants, and then you have one central inverters here. And then you can see here, this is the transformer for grid connection. Okay. You see, this is the panel from inside. So how it looks like. So it's huge, you know, center for the central inverters. You see the string, you know, you can see here 1, 2, 3, 4, 5 different strings, you know, and different. This is SME strings, you know, so grouped together and then they're being connected, you know, together. Okay, so then the problem. Let me talk about the This is how the microinverter looks like. You see, this microinverter actually can be placed at the back of the panel itself. Okay, so it is a standalone, and it can be attached. What you get here is AC directly. So this is what is inside. It's very, very compact. Okay, and is dedicated to each shuffle the panel. So I think maybe it's the time, Mr. Siva?
Yes, Dr. You can stop over here.
Okay, maybe we can take maybe 1 or 2 questions before we stop. I just want to show you some of the actual systems, actually, how they look like, you know. So I hope that's any questions?
Any questions?
I think because usually we do 30 minutes questions, 30 minutes questions, 30 minute questions. So I hope that I think we have answered a couple of questions. So if additionals, otherwise you can ask them tomorrow.
Yeah. Tomorrow we'll have a session at 8:13 a.m. in the morning, sir. Or shall I need to change anything as per the Australian timings?
What about MPPT in central inverters? Unfortunately, MPPT in central inverters does not work. Okay, because MPPT is meant to address the you know, but central inverters usually will not operate on MPPT. Impossible. Sorry,
Professor, are you
Yes.
able to see my screen, Professor?
yes.
Yeah, tomorrow the schedule is at 2 p.m. right? Is there anything like to change?
So 2 p.m. here.
It is fine, right?
Yeah, it's fine. Yeah.
Okay, Professor.
All right. Okay. So thank you very much for attending, and see you tomorrow. And please, if you have questions before tomorrow we start, because we are going to continue this topic. So please, if you have any questions, you know, write them, put them, and then tomorrow we will ask them. Okay. Thank you very much.
Yeah, thank you, Professor.
Thank you. Take care. Thank you very much. Okay. Have a great day. You know.
Yeah. Thank you.
Thank you.